Hello everyone, welcome to this lecture on permutations and combinations. Today in this lecture, we will cover NCERT exercise 6.2 and NCERT sections 6.3.3 and 6.3.4 and NCERT example 9. So let's get started. This is disclaimer. So in this lecture, we will first cover NCERT exercise 6.2, question number 1 to 5. After that, we will look at derivation of formula for NPR. Then we will find permutations when all the objects are not distinct objects. Then we will solve NCERT example 9. So I hope you are ready to start. Okay, so make sure you are with your notebooks and pens ready. So let's get started. First, NCERT exercise 6.2. Look at question number 1. In this question, we need to calculate 8 factorial and 4 factorial minus 3 factorial. So let's start the solution of this question. Here we have n is equal to 8. So using the formula n factorial is equal to n times n minus 1 times dot 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 3 into 2 into 1. Okay, so we can calculate the value of 8 factorial using this formula of factorial. Okay, so 8 factorial means multiplying all numbers from 8 to 1, and its value will be 40,320. Okay, so 8 factorial is equal to 40,320, and here basically we use this formula n factorial is equal to n times n minus 1 times n minus 2 dot 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 3 into 2 into 1. Now we have calculated here 8 factorial is equal to 40,320. Now let's look at the second part of this question. So when n is equal to 4, then we get 4 factorial. So 4 factorial means multiplying from 4 to 1, and its value will be 24. Okay, since we know the formula n factorial is equal to n times n minus 1 times dot dot 3 into 2 into 1. Then let's calculate 3 factorial. Okay, so take here n is equal to 3, then we get 3 factorial. This is equal to 3 into 2 into 1 is equal to 6. Okay, now we can calculate the value of 4 factorial minus 3 factorial. Okay, so this is 24 minus 6, which equals 18. Clear? So 4 factorial minus 3 factorial, this is equal to 24 minus 6 is equal to 18. I hope it is clear to all of you. So now let's move to the next question. This question asks whether 3 factorial plus 4 factorial is equal to 7 factorial. Okay, it's true. Okay, so we have to verify, or we have to check, is 3 factorial plus 4 factorial is equal to 7 factorial. So let's solve this question step by step. Here n is equal to 3. Okay, so using the formula n factorial is equal to n times n minus 1 times dot 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 3 into 2 into 1. Okay, so 3 factorial means here 3 into 2 into 1. Okay, so which equals to 6. When n is equal to 4, then we get 4 factorial. Okay, 4 factorial means 4 multiplied by 3 multiplied by 2 multiplied by 1. Okay, which equals to 24. Now we add 3 factorial and 5 factorial. So 3 factorial plus, now we add 3 factorial and 4 factorial. So 3 factorial plus 4 factorial becomes 6 plus 24, and which is equal to 30. Okay, so 3 factorial plus 4 factorial is equal to 30 when n is 7. Okay, so using the formula, n factorial is equal to n times n minus 1 times dot 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 3 into 2 into 1. Okay, so 7 factorial is equal to 7 multiplied by 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Okay, which equals 5040. Finally, we can see that the value of 3 factorial plus 4 factorial is 30, which is not equal to 7 factorial, which is 5040. Therefore, 3 factorial plus 4 factorial does not equal to 7 factorial. Clear? So I think it is clear to all of you. So now let's move to the next question. Here in this question, we have to calculate 8 factorial upon 6 factorial into 2 factorial. Okay, so we will calculate this by simplifying. So let's solve this question step by step. So we need to evaluate 8 factorial upon 6 factorial into 2 factorial. Now, we will use the formula n factorial is equal to n times n minus 1 times n minus 2 into dot 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 3 into 2 into 1. And we know the important property, n factorial is equal to n times n minus 1 factorial. Okay, so we get here 8 factorial upon 6 factorial into 2 factorial. This is equal to 8 into 7 into 6 factorial upon 6 factorial times 2 into 1. Okay, so here 6 factorial will be cancelled out, and then you will get the simplest form of this expression. So cancel out 6 factorial, we get 8 factorial upon 6 factorial times 2 factorial. This is equal to 8 into 7 upon 2 is equal to 28. Okay, so let's take a moment to ensure we understand each step. Okay, so we have simplified the expression by cancelling common terms. Okay, and performing basic arithmetic to simplify this. So this is a crucial step to solve permutations and combinations problems efficiently. Okay, so let's now move to the next question. Okay, so in this question we have the equation 1 by 6 factorial plus 1 by 7 factorial is equal to x upon 8 factorial. Okay, and we need to solve this to find the value of x. So let's start the solution step by step. Here we need to calculate the we need to we need to find the value of x. Okay, so we have given here the equation is 1 by 6 factorial plus 1 by 7 factorial is equal to x upon 8 factorial. Okay, so here we can use the formula n factorial. This is equal to n times n minus 1 factorial. Okay, so 1 by 6 factorial plus 1 by 7 into 6 factorial. Okay, this is equal to x upon 8 into 7 into 6 factorial. Since here 1 by 7 factorial can be written as 1 by 7 into 6 factorial. Okay, so now you can simplify it and get the, here you can take the common 6 factorial in left hand side, and we get 1 by 6 factorial times 1 plus 1 by 7. This is equal to x upon 8 into 7 into 6 factorial. Okay, and here you can see 6 factorial is common in denominator in left hand side and right hand side. You can easily now cancelling them. So the equation becomes, after cancelling 6 factorial, 1 plus 1 by 7 is equal to x upon 8 into 7. The equation simplifies to give us 8 by 7. This is equal to x upon 8 into 7. Finally, the value of x will be 64. Clear? I think it is clear to all of you and you are getting my point. Now, in this question, we need to evaluate n factorial upon n minus r factorial when we have given in the first part n is equal to 6 and r is equal to 2. And in the second part, we have n is equal to 9 and r is equal to 5. So let's start the solution for this question step by step. So when n is equal to 6, r is equal to 2, we get n factorial upon n minus r factorial. This is equal to 6 factorial times 6 factorial upon 6 minus 2 factorial. This is equal to 6 factorial upon 4 factorial. Using the formula n factorial is equal to n times n minus 1 factorial, we can write 6 factorial as 6 into 5 into 4 factorial, and 4 factorial gets cancelled out in numerator and denominator, and this way we get its value is 30. So therefore 6 factorial upon 6 minus 2 factorial, this is equal to 30. Now let's continue the solution from here. When n is equal to 9 and r is equal to 5, then n factorial upon n minus r factorial will become 9 factorial upon 9 minus 5 factorial. This is equal to 9 factorial upon 4 factorial. Here we can write 9 factorial as 9 into 7 into 6 into 5 into 4 factorial. As we know the formula, n factorial is equal to n times n minus 1 factorial. Okay, so here are 4 factorial in the denominator. Okay, and it will be cancelled out to each other. So now here the value of n factorial upon n minus r factorial is equal to 9 into 7, 9 into 8 into 7 into 6 into 5. This is equal to 15,120. So the answer will be 15,120. Okay, so when n is equal to 9 and r is equal to 5, then n factorial upon n minus r factorial will be 15,120. I hope it is clear to all of you. Now we will explore some theory. Okay, so let's start. So look at here derivation of the formula for NPR. So here we will look at for formula NPR. So how NPR comes, okay, and what is the formula for NPR, we will discuss now. So here let's see the formula here. The number of permutations of n different objects taken r at a time is basically NPR. Okay, so NPR means the number of permutations of n different objects taken r at a time. Okay, so NPR, this is equal to n factorial upon n minus r factorial, where 0 less than equal to r less than equal to n. So let's prove it. Now we move towards the proof, and we will try to understand how this formula come. Okay, so we know that NPR, this is equal to n times n minus 1 times n minus 2 times dot 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 n minus r plus 1. Okay, so look at this pattern carefully. So this is a sequence that is used to arrange objects. Okay, so already we know this formula for NPR. Now we multiply and divide by n minus r into n minus r minus 1 into dot 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 3 into 2 into 1, which is basically n minus r factorial. So we get NPR, this is equal to n times n minus 1 times dot 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 n minus r plus 1 multiplied with n minus r factorial upon n minus r factorial. Okay, so this step is very crucial step because it helps us bring the numerator into factorial form. Okay, so now the numerator n times n minus 1 times dot 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 n minus r plus 1 dot dot into n minus r dot 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 into 3 into 2 into 1, which is simply n factorial. Okay, and finally we get the formula NPR is equal to n factorial upon n minus r factorial. Okay, so this derivation is complete now. Now we can easily calculate permutations using this formula. Okay, so now you should keep in your mind this formula NPR is equal to n factorial upon n minus r factorial, where 0 less than equal to r less than equal to n. So I hope this formula and derivation of this formula is clear to all of you. Now we understand special case for NPR. Okay, so the special cases the number of permutations of n distinct objects taken at a time taken at a time is NPN is equal to n factorial upon n minus 1 n minus n factorial. Okay, so here in this special case, here you can see when you find the number of permutations of n objects taken all at a time, then in this case NPN this is equal to n factorial upon n minus n factorial. Basically here we use we use the formula NPR is equal to n factorial upon n minus r factorial. Okay, and here r is n. Okay, and we get here n factorial upon n minus n factorial. Okay, so here n minus n factorial is nothing but equal to 0 factorial. Okay, and we know that 0 factorial is equal to 1. Clear? So this is equal to n factorial upon 0 factorial. Since 0 factorial is 1, so in denominator it will be 1, and this is simply equal to n factorial upon 1, and this is equal to n factorial. Okay, so NPN this is equal to n factorial. That means the number of permutations of n distinct objects taken all at a time is n factorial. I hope this special case is clear to all of you. Okay, now look at theorem 2. Okay, so here theorem 2 states that the number of permutations of n different objects taken are at a time where repetition of objects is allowed is n to the power r. Okay, so which represents the total number of possible arrangement. Okay, when you have n different objects and you are arranging r object at a time. Okay, that means the number of permutations of n different objects taken are at a time, and here the repetition of objects is allowed. Okay, so for r different vacant places you have n choices for each. Okay, so the total number of permutations of n different objects taken are at a time is n to the power r. Now let's forward to proof. Okay, so here if we have n different objects and we need to arrange our objects from them, then and repetition is allowed, the number of permutations will be n to the power r. Okay, so now we are going to prove it. So now we will look at the proof of this theorem. So here you can see the task is to fill r places, and for each place we have n choices since objects can be repeated. Okay, so to fill the first place we have n choices. Okay, so the first place can be filled in n ways. Since repetition is allowed, so the second place can also be filled in n ways. Okay, so look at the look at this pattern carefully. This pattern applies everywhere. Okay, that's why we have used dots here, dot, and let's continue this process. Finally, the nth place can also be filled in n ways. Okay, so for each place, okay, for nth place we have n choices for each places. Okay, so what we have done so far, so we have find the choices for first place, second place, and nth place. Okay, so now what can we do? Remember now multiplication rule. So multiplication rules states that if there are m ways to do one task and n ways to do another task, okay, then there are m into n ways to do both tasks together. Okay, so now we are going to applying this rule to find the number of permutations of n different objects taken at a taken are at a time. Okay, so therefore the total number of permutations is basically equal to n times n times n dot n. Okay, r times. Okay, so r times here n multiplied, so this is nothing but equal to n to the power r. Okay, so the number of permutations of n different objects taken r at a time where repetition of objects is allowed is n to the power r. I think how we get this, that you understand. Okay, so now let's look at an example problem. Okay, so here in this example we ask us how many three digit numbers can be formed from the digits 1 2 3 4 5, assuming that repetition of the digits is allowed. Okay, so let's see here. This example is about how many three digit numbers can be formed from the digits 1 2 3 4 5, and here assuming the repetition of the digits is allowed. So let's solve this example step by step. So first let's see what we have given. Okay, so in this example we have given that the digits 1 2 3 4 5. Okay, and we have to find number of three digit numbers formed by the from the digits 1 2 3 4 5, and assuming repetition of the digits is allowed. Okay, so here n is equal to 5, so 5 digits we have given. Okay, so 5 digits available here, so we can use these 5 digits and we can construct three digit numbers. So how many three digit numbers we can form, that we need to find here. So here three we have three places to fill. So R is equal to 3. So what we have done so far, so we have 5 digits and 3 positions to fill. Okay, and repetition of the digits is allowed here. Okay, so let's find how many digit numbers can be formed from the digits 1, 2, 3, 4, 5, assuming that repetition of the digits is allowed. So therefore, by theorem 2, okay, theorem 2 said us the number of permutations of n different objects taken r at a time where repetition of objects is allowed is n to the power r. Okay, so here n is 5 and r is equal to 3. So simply substitute here the values of n and r in this formula. Okay, then you will get the answer. So let's apply this theorem to get our answer. So we have here n is equal to 5 and r is equal to 3. So how many digit numbers can be formed? So finally we find the number of 3 digit numbers that can be formed from the digits 1, 2, 3, 4, 5, assuming that repetition of the digits is allowed. Okay, that is 5 to the power 5 cube. This is equal to 125. Therefore, the number of 3 digit numbers using 1, 2, 3, 4, 5 is 125. So I hope this example is clear to all of you. Now, let's see theorem 3. Okay, so theorem 3 states that the number of permutations of n objects where p objects are of the same kind and rest are all different, okay, is n factorial upon p factorial. So focus on this theorem, okay, and how we can prove it, that we will see. So let's do the proof of theorem 3. So first here we will assume all objects are distinct. Okay, so the total number of permutations would be n factorial. If we consider p identical objects, okay, and rest are different. So if they were distinct, they could be arranged among themselves in p factorial ways. Since they are identical, so all these arrangements look the same. Okay, so to correct for this overcounting, we must divide the total number of permutations n factorial by p factorial. Okay, so therefore the number of permutations of n objects where p are identical and rest are all different is n factorial upon p factorial. Okay, so I think this theorem is clear to all of you. Okay, so now let's move to the next one. So in this slide we will see theorem 4. Okay, so theorem 4 states that the number of permutations of n objects where p1 objects are of the first kind. Okay, first kind means p1 objects are the identical object, that is first kind, and p2 are the second kind identical objects, and pk are the kth kind. Okay, and the rest, if any, are of the different kinds, is basically n factorial upon p1 factorial into p2 factorial into pk factorial. So let's do the proof. So first, let's assume all objects are distinct. Okay, so if all objects were distinct, then the total number of permutations would be n factorial. Now consider P1 identical objects. Okay, if they were distinct, then they could be arranged among themselves in P1 factorial ways. Since they are identical, all these arrangements look the same. So to correct it for overcounting, we divide the total permutations n factorial by P1 factorial. Therefore, n factorial upon P1 factorial. Okay, so we have the formula for permutations is n factorial upon P1 factorial. We repeat this division. We repeat for every identical group like P2 factorial, P3 factorial, etc. After finally, we get the final formula n factorial upon P1 factorial into P2 factorial into dot 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 Pk factorial. Okay. Now let's look at an example. So in this example, we have to find the number of permutations of the letters of the word institute. Okay. So let's see how to solve this example. So let's solve this example step by step. Look students, here we have total 9 letters in institute. Okay. Here identity letters I appears 2 times. So P1 is 2. T appears 3 times. So P2 is 3. The other letters N, S, U, E are distinct letters. So by using the theorem 4, the theorem 4 tells us the number of permutations of n objects where P1 objects are of the first kind, P2 are the second kind, and dot dot Pk are the kth kind, and the rest of the given objects are different kinds. Then the number of permutations is n factorial upon P1 factorial into P2 factorial dot 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 Pk factorial. The total arrangement for the given word institute is 9 factorial upon 2 factorial into 3 factorial. So here we are using the formula n factorial is equal to n times n minus 1 factorial. So here 9 factorial can be written as 9 into 8 into 7 into 6 into 5 into 4 into 3 factorial. Okay. So this is equal to 9 into 8 into 7 into 6 into 5 into 4 into 3 factorial upon 2 factorial into 3 factorial. Now we again use the n factorial is equal to n times n minus 1 into n minus 2 into dot 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 3 into 2 into 1 this formula, and we get this is equal to 9 into 8 into 7 into 6 into 5 into 4 upon 2, and this is equal to 9 into 8 into 7 into 6 into 5 into 2, and after calculating you will get this is equal to 30,240. Okay, so final answer will be our 30,240. So therefore number of permutations of the letters of the word institute is 30,240. Okay, so I hope this example is clear to all of you. Now let's look at another example. So in this example we have to find the number of permutations of the letters of the word Allahabad. Okay, so let's see how to solve this example. So look at here. Here we have to find the number of permutations of the letters of the word Allahabad. Okay. Here there are 9 objects, of which there are 4 A's and 2 L's, and rest are all different in Allahabad word. So let's think about. Okay, we have 4 A's similar identical. Okay, and 2 L's identical. Okay, so which theorem you can use here to find the number of permutations of the letters of the word Allahabad? Think about this. So here using theorem 4. So theorem 4 states that when when we have n objects, okay, where p1 objects are of the same kind, p2 are the second kind, and the pk are the kth kind, and the rest, if any, are the different kinds. Okay, is n factorial upon p1 factorial into p2 factorial pk factorial. So this formula gives us the exact number of permutations for the letters of the word Allahabad. So we have n is 9, p1 is 4, and p2 is 2. So now 9 factorial upon 4 factorial into 2 factorial, this is equal to 9 into 8 into 7 into 6 into 5 into 4 factorial upon 4 factorial into 2 factorial. Since we know the n factorial is equal to n times n minus 1 factorial. And we know n factorial is equal to n times n minus 1 into 3 into 1. So this is equal to 9 into 8 into 7 into 6 into 5 upon 2 into 1. And after simplifying, we'll get this is equal to 7560. Okay. So finally, we get the answer 7560. So these are the total permutations that we can make from the letters of Allahabad. Therefore, the number of permutations of the letters of Allahabad is 7560. I think this example is clear to all of you. So students, that's all for today's lecture, and thank you very much to all of you.